Welcome to Chapter 6 of the Artificial Intelligence book, Constraint Satisfaction Problems. In this chapter, we're going to step up in our level of ability to solve interesting problems using computer logic or artificial intelligence. You can see a few constraint satisfaction problems on the screen here. A map coloring problem. If we only want to use 4 colors to color in every state in the country with no 2 adjacent states the same color, how can we do that? Can we do that? You see the n-queens problem down at the bottom that we've used for the past couple of chapters. How can we place those queens so that no 2 are constrained or conflicting? And the same thing with the Sudoku puzzle. We're trying to get all 9 digits, 1 through 9, in each of those 3x3 squares and in each row and column, and use each number only once in each of those settings. So the 8 that you see in the upper left corner can be the only 8 in that block of 3x3 in the upper left, the only 8 in that row across the top with the 8, 4, 6, 7, and the only 8 in that column with the 8, 5, and 3. And we want to use all 9 digits in each one of those settings. So let's look at how we define constraint satisfaction problems. Well, first of all, we start with a state that's defined by variables and values. The variables, such as each of the states in the previous page here, tell us what we're trying to assign values to. The values can be the colors for the map problem here. The variables in the Sudoku puzzle are the positions on the board, and the values are the numbers 1 through 9. And for the n-queens problem, the variables could be the queens themselves, and the values would be the locations. Or we can look at it a different way and say that the board locations are the variables, and whether there's a queen or not are the values. So the state of a constraint satisfaction problem is defined by its variables, and we'll call those x, and the values that we choose from some domain D. So the values, once again, for the map coloring problem would be the colors, the 4 colors that we want to use. The variables would be the states themselves. As our goal test, we know that we've solved a constraint satisfaction problem when we can test that set of constraints and make sure that all of them are satisfied. So we find a combination of variables and values that satisfy all of the given constraints. Tennessee and Georgia can't be the same color for the map coloring problem. There can only be 1 8 in the upper left corner of that board. The solution is any complete and consistent assignment. That means we don't violate any of the constraints in the problem. So how does this compare to the search problems we've been looking at the last couple of sections? Well, first of all, a standard search problem state is a black box. We can apply any data structure, any algorithm, any heuristic function and goal test that gets us a search tree, a solution for the problem that we're looking at. With CSPs, we have a more structured representation for states. For example, Tennessee equals red, or Georgia equals green, for example. And we use the formal representation language. So we start to specify constraints, values, and variables in a particular way for different constraint satisfaction problems. Third, a constraint satisfaction problem allows a more useful general purpose algorithm with more power than our standard search algorithms. We can solve more and more interesting problems. So here's a simple example. Map coloring. If we want to color this map using no more than, let's say, 3 colors for this particular example, then how would we approach that? Well, we have some variables: Western Australia, the Northern Territory, Queensland, New South Wales, Victoria, South Australia, and Tasmania. And then we have some domains. Let's say we want to use the 3 colors, red, green, and blue. That's our domain. We have those values, red, green, and blue. So what we're after is a consistent assignment of red, green, and blue to each of the variables, Western Australia, Northern Territory, and so on, so that no 2 adjacent colors match, right? It makes sense that when we're coloring the map, we wouldn't want both Western Australia and the Northern Territory to be red. They would look like one state, correct? So the constraints are adjacent regions have to have different colors. In other words, we would formalize that or represent it in language mathematically as WA, Western Australia, is not equal to NT. So whatever the value of Western Australia is, red for example, cannot be the same as the value that we store in the variable Northern Territory, or NT. So red and green would satisfy those two, red and blue, green and red, and so on. But we cannot have the same color or the same value in two adjacent areas of the map, or two variables. So this would be a complete coloring, a consistent coloring of the map of Australia. Western Australia is a different color from Northern Territory, and so on all the way around. You can see South Australia there is our only blue state, and it constrains all those other values. We can't have another blue state except possibly Tasmania as we get off the continent there, the main continent. We can represent most of our constraint satisfaction problems with a constraint graph. In fact, this is the most common type that we'll see, and it's what we'll be using in this course. So a binary constraint satisfaction problem is one where each constraint can relate two variables. So if we draw a constraint graph like the one you see on the screen here, our nodes are the variables, Western Australia, Northern Territory, South Australia, Queensland, all around. And then our arcs are the constraints. So Western Australia can't be the same color as Northern Territory, and so on. So we can represent these types of constraint satisfaction problems, or we will represent these constraint satisfaction problems with a constraint graph where we have binary constraints. So we would count each edge or each arc between those nodes as a constraint. You can't have WA equal to NT. In the next section, we're going to see a few different types of constraint satisfaction problems and different constraints that we can impose on variables in a problem.